In this class, we're going to look at how to solve circular functions, starting with the basics of just looking at where the circular function exists on our unit circle, and then building up to the more complicated examples until finally looking at how to generalize the solution across all possible domains. Enjoy! Okay, let's make a start. So, for this class, we're going to continue on with the circular function stuff we did last week. So specifically, we're going to be looking at solving circular functions, which means you're given the exact value that the circular function is equal to, and you have to figure out the angle that's associated with that. We then look at how to generalize that for all iterations around the unit circle, and then finally we'll have a look at how to solve inequality versions of those kinds of equations. Okay, so yep, all screen shares are good. Let's go. So, in all cases, solving circular functions is effectively a four-step process like this. That's just a bunch of text on a screen. Let's try a few examples and apply it to those. So here's a pretty textbook example of how of a question that might come up. We're just looking for where cos is equal to root 2 on 2, and we're solving for a particular domain, in this case from 0 to 2 pi inclusive. First step is pretty much the first step of a lot of these kinds of questions, which is just rearrange to make sure we have something that we can work with. In the case of circular functions, we want what's known as an exact value expression, which means circular function on one side, exact value on the other. We already have that, so no need to do anything there. From there, if it's a bit more complicated, if you have a composite function, so anything other than just x, inside of that cosine, then you would possibly use a substitution approach to simplify things down, but we don't have that yet. That'll be in the later examples. From here, we just want to look and figure out where is cosine equal to root 2 over 2 on the unit circle. Where are all those spots within the given domain? In this case, root 2 over 2, cosine being x, we're looking for where the x's are equal to root 2 over 2, which is going to occur at pi over 4 and 7 pi over 4. Our domain was 0 to 2 pi, so we are doing just that one revolution, which is why we're going to just stop there. Pi over 4, 7 pi over 4. Step 4 only applies if step 2 had applied, which in this case it did not. That's fundamentally all we ever do. The remaining example is just going to be slightly more complicated versions of that. Like, for example, if you have to rearrange, you have this kind of equation here. And while technically 0 is an exact value on the unit circle, there are those coordinates 1, 0, 0, 1, all of those. The fact of the matter is we don't have the circular function on its own. We need both of these things to be true, which is why we would add root 3 and divide by 2, thus getting what we're looking for. From there, we look for where all the y values are root 3 over 2. Y values because it's sine rather than cos. That's going to be the pi over 3 and the 2 pi over 3 respectively. If there's any questions at any time, feel free to interrupt me. If you have different domains, so we're not doing 0 to 2 pi anymore, we're doing negative pi to pi, we essentially break it down into a positive half and a negative half starting at 0. So the first iteration we'll just do from 0 to pi, and the second go through will do 0 to negative pi. So we want to figure out where is sine equal to 0. That's going to occur at these highlighted spots here. It's just where the y value is equal to 0. Now from 0 to pi, that means the first go around means we're only looking at this top half of the unit circle. Under which circumstances y equals 0 at x equals 0, well, at the angle equals 0 and the angle equals pi. So that'll be the first two solutions on that first go around. Now on the second go around, 0 to negative pi means we're doing this bottom half, but we're doing it in the opposite direction. We're going in a clockwise motion rather than an anti-clockwise motion. So we've already hit the 0 from before. We don't have to say 0 again, although you could if you wanted to. But when you get to this spot, which was pi, because you're going in the negative direction, you now say negative pi for that one. So for that reason, in total, you had negative pi, 0, and pi as all those solutions for that circular function. I know that gets people a little bit weird sometimes, so if you have any questions around that, let me know. This one definitely gets people weird, which is when you have a whole bunch of stuff, or even just a little bit, inside the brackets of your circular function. Under these circumstances, I consider this a composite function. And so step one is still going to be to get your exact value thing. You just want to have cosine on one side, exact value on the other. That's not so bad. What comes a bit weird is when you've got all this stuff in here, you don't strictly have to do this, but I've found that it's the easiest way to work with it, which is you take whatever's in the brackets and you replace it with u, or just some letter, doesn't matter what the letter is. Now, the reason why we do that is because you look at this, that looks nasty. If you were to look at this, that's significantly less nasty to look at. It just makes it a bit nicer. And so one of the things you have to watch out for when you do this substitution is you have to fix up that domain. So we have to solve it for 0 to 2 pi. If we're going to do that u substitution, it means that we're going to replace this domain purely in terms of u instead. The reason why this matters is because, like, particularly dilation factors and a little bit with the translation factor will greatly change the amount of solutions you expect. Normally, circular functions will max out at 2 solutions between 0 and 2 pi. If you have any dilation factors, that could double or even triple depending on what that factor was, or potentially half, again, depending on what the factor was. It'll modify the number of solutions. Furthermore, if you have a pretty drastic horizontal translation, that could also impact the number of solutions, but it really all depends case by case. So to avoid all of the complexities around that, that's why we do this substitution and we replace our domain. The way that works is you take the x values from your domain, so x value of 0, x value of 2 pi, and you chuck those into that equation with u in it. If you replace the x's with those 0s and 2 pi respectively, you're going to get the new effective domain for the thing you're trying to solve. Once you get it to this stage, you just treat this like you've always treated solving circular functions. There's no weirdness around dilation factors or translation factors. You just want to solve where cos is a half for that given domain. Cos is a half at pi over 3 and 5 pi over 3, and we're just going to keep smacking 2 pi's on the end of that until we exceed our domain restriction. We want to cap out at 9 pi over 2. If you keep adding your 2 pi over and over again, it could pay off if you notice that you have a pretty common denominator, like in this case it's all denominators of 3. It would pay off to try and get a common denominator between your upper bound and your solutions. That way you can more easily compare where to actually cap out.
Chris?
Yeah?
Shouldn't the upper bound of our domain be 5 pi over 2?
Should it be 5 pi over 2? Why is that?
Because the original domain was 2 pi, and then plus pi over 2 would be 5 pi over 2. Oh no, we distributed, my bad, sorry.
We put it in here, yeah.
Yeah, right.
Yeah, no, you're good. It's good to, because there are, like, I've seen like minor little things that could be issues there, so it's good that you keep a lookout. But yeah, that one's clean. But yeah, okay, so we get our full list, and then all we're going to do is trim that list. So if you go too far, that's fine. All you've wasted is a bit of time. And so you just compare your lower bound and your upper bound to what your list is. In this case, pi over 3 is too small. We want to have a lower bound of pi over 2, so we're going to kill that one. And then this one's a bit too big, so we're going to kill that one. That's going to shrink that list down. And the basic rule of thumb is look at the coefficient on your x, in this case it's 2, and look at your domain. So for every 0 to 2 pi, or gap of 2 pi, you would expect 2 solutions, roughly speaking. If you have a coefficient of 2, you would double it. If you have a coefficient of 3, you would triple it. That's more of a rough guess as to how many solutions you should have, because this translation factor may or may not knock one off. But yeah, you have that list. You can be pretty safe with saying that that is in fact the list of values that you have. And so all you'd have to do is, instead of writing these purely in terms of u, you'd write them back in terms of x instead. So u equals this becomes 2 bracket x plus pi over 4 equals all of that. Now, this is probably one of the more complicated ones you'll come across. In this case, you need to do a division of 2 on everything here, and then a subtraction of pi over 4. For Unit 1 and 2, usually they make this translation term like an easy addition or subtraction. In Unit 3 and 4, they will give you, well, they're more likely to give you different denominators, so you have to work a bit harder to do those subtractions or additions. But yeah, fundamentally that's it. You can see that if you do this substitution method, you'll see that everything fits within the domain that was originally prescribed to us, 0 to 2 pi. So there's no guessing involved with how many more solutions you need. That's probably the most complicated of all these examples, so feel free to let me know if there's any questions. Otherwise, there's a few more niche examples. These are more likely to come up on an exam, where one of which is you can solve by null factor law. So what's interesting here is when you have cos squared and cos, there's a common factor of cos there. And so if you were to factorize that, what you would get is a factorized equation that equals 0. Null factor law doesn't only apply to polynomials. It applies every time that you have a product of two things that equal 0, which is why you can now say cos equals 0 or cos plus 1 equals 0. And so you just solve both of those individually. Cos is going to be 0 in these spots. Cos plus 1 equals 0 becomes cos equals -1, which is just that spot there. And so you just add, well not add, but just put a bunch of commas between all of those spots, or all those angles rather. Another pretty common thing is to convert to tan. You can do this typically when you have both sine and cos in your equation. Fundamentally, all you're doing at some point in your simplification is to divide both sides by the cosine term, whatever that is. In this case, it's cos 2x, so you would divide both sides by cos 2x. You can do that immediately if you want, or you can chuck things the other side initially. It's really up to you there when you want to do that. Point being, when you divide that both sides by cos 2x, the cos 2x term itself will cancel down to just 1, or at least in this case, -1. And then when you do sine divided by cos, that's just tan. So you get it down from having two circular functions to just one. From there, you rearrange that, and then you just solve. Now, tan, probably a little bit harder to solve, not because you do anything differently, but because it's a bit rarer to solve. So we need to figure out where is tan equal to -1 over root 3. It does end up being these spots here. If you just know that from your tan unit circle, or otherwise have practiced those values, then that's good. If you're going down the route like I did in school, which was just remember sine divided by cos, then you've got to do a bit of math to figure out what values of sine and cos give you -1 over root 3. And that would be when you divide a half by -root 3 over 2. So if you know that's the pairing, then you just look for where a half and root 3 over 2 are, the cos and sine respectively. And because it's negative, you'd have to have one of those values be negative. So a bit more workaround. I don't necessarily recommend that anymore, but it is what I did in school and it worked out enough. But yeah, so you just hit all those values. In this case, because we had 2x and we're solving from 0 to 2 pi, we would expect roughly 4 solutions. I kind of glossed over it here, but because we had 2x in here, I did do that substitution thing. We had 0 to 2 pi. We now have 0 to 4 pi because of that. So that's how we've ended up with 4 possible solutions there. And once again, those are in fact between 0 and 2 pi. That's about it for solving circular functions, specifically when you have a restricted domain, a very targeted domain. Any questions there? I'll take a pause. General solution is going to be a very similar circumstance. Fundamentally, all we're doing here is looking at what happens when there's no domain associated. Under those circumstances, you have to give what's known as the general solution, which is a specific way of writing your solution such that it encompasses all possible solutions for all possible revolutions of the unit circle. A lot of the steps are going to be the same. You want to get your exact value expression, you might need to do a substitution, and you're going to find your first two solutions, or at least just find where it's equal to, in this case, negative root 3 over 2. So sine is negative root 3 over 2 at those two spots, so that's going to give you your first two solutions. Here's where it gets slightly different. To account for every other possible revolution, you just slap plus 2 pi n onto each of these terms. That's pretty much it. So you got the 4 pi over 3 and the 5 pi over 3. You just put a 2 pi n onto each of those. If you want to be super specific, you could say that n is an element of z, z being the integers. That way it's like pretty much as bulletproof as you could write that, but yeah, that'd be more for safety, I guess. That's pretty much it. The only part where this gets a bit weird is the order operations if you have like a 3x in this case here. So exact same approach, more or less. We're looking for where sine is negative root 3 over 2. Once again, same values. The order of operations here is to add your 2 pi n first and then rearrange for x. That's really the only nuance you need to be aware of there. So you add your 2 pi n first, replace the u with 3x, and then divide everything by 3. So your 2 pi n also gets hit by that. That's pretty much all you need to know. If you want to go further and know some further simplifications, that's when we can look at these further examples here. So we've already covered pretty much everything you would need to know at a minimum. This is just going a bit further to show or demonstrate a bit more skill if you're looking for like a significantly higher study score. That way your answer is a bit more competitive with those people. So first up, where's cos equal to negative root 3 over 2? Well, you find those two spots, you stick your 2 pi n there, and you're mostly good. Now, if you want to go above and beyond to simplify that even further, one thing to notice about cosine is that its solutions are always vertical from each other. Or another way to say that is one is the reflection of the other. So another way to write this would be positive 5 pi over 6 and negative 5 pi over 6. And so that gives you a nice little neat simplification, which is to say, instead of having two separate equations and then say n is an element of integers, you can just knock one of those down and stick a plus minus on your 5 pi over 6. It's an equivalent way of saying the same thing. And that demonstrates a bit more skill in your math, should you wish to do that. And then for tan has one as well. Largely speaking, you'll do the same steps. Root 3 is going to be at these two spots here, pi over 3 and 4 pi over 3. You'll do your 2 pi n, and that'll be enough. But if you want to go a little bit more above and beyond, you'll notice that any set of tan solutions are always separated by pi from each other. And so what that means is, instead of doing just 2 pi n to both of these, you can knock one of these off and do pi n instead. Like for instance, if n was equal to 1 here, you'd have pi over 3 plus pi. That is 4 pi over 3. So it already accounts for it if all you do is drop that coefficient off of the pi n there. So it's a more slightly more sophisticated general solution there. But again, to reiterate, if you don't want to memorize all that stuff, you don't have to. Just stick to the framework. Don't feel like you have to simplify this unless you really want to shoot for those higher study scores. That's about it there. Once again, I'll take a pause for that one. Anything to clarify for those? This one is super niche. I've only seen it in like one subsection of the Unit 1 and 2 book, and that's when you have solving inequalities. This doesn't appear in Unit 3-4, and I've only ever seen a tech active version of this in a real exam. I'm showing you a tech free version just because that did in fact appear in one of the Unit 1 and 2 ones. You're still solving, or you're still following mainly the same steps, which is get your exact value expression. So in this case, we just got an inequality there. Only thing to watch out for here, of course, would be any multipliers or divides by negatives. Those will cause it to flip direction. From there, domain is 0 to 12. We've got pi over 6t, so we're just going to do a quick substitution there, and that's going to give us a nice and neat cosine is greater than or equal to half for 0 to 2 pi. Now, one of the things that would be good to do is start by identifying what I call the breakpoints, which is where does cos equal 0? Cos equals 0 vertically here from pi over 2 and 3 pi over 2. Now, that only gives you a starting point. We want to figure out where cos is greater than or equal to 0. So that could be any value from 0 to 1. Can't go any further because the unit circle caps out at 1. And so what that basically means is where is my x values positive or 0? That's going to be the entire right-hand side of the unit circle. So the way you would give this as a domain is you would say that u, because we did that substitution, is going to be between 0, the angle, and pi over 2. Remember, we do these things in terms of angles. 0 to pi over 2, and then another section, 3 pi over 2 to 2 pi. All you'd have to do from there is once again get everything back in terms of, well, in this case it's t. So again, you're going to replace all these u's with those values, and then rearrange for t each time. You'll see a pattern. There's usually always a pattern. So if you see you're going from 0 to 3 to 9, you can, maybe skip some steps a little bit, but that's a bit risky. But yeah, that's pretty much it. I do have a quick note in here, and that is that the CAS does tend to struggle a little bit with solving circular function inequalities, even if you do restrict your domain. And what I mean by that is when you do a CAS solve specifically. So the recommendation instead is to actually graph it and solve it graphically. So you restrict your window size for whatever that circular function is, and then you just set you imagine or draw on the CAS the bound of which you want to be up or above or below. So in this case, we wanted to be above or equal to 0. That should say or equal to 0. And so you could solve for where effectively your x-intercepts are, and you can visually just see we're going from 0 to 3 and 9 to 12. That's if you get a tech active version. I've drawn these vertical lines just for visuals. You don't have to have drawn these in yourself. You can just do the graphing tool for, I think it's roots on the Casio, and it's 0 on the TI Nspire. Yeah, that's about it. If you have multiple cycles, you just do the same thing, but duplicate your effort. So if you want to look at where sine is greater than a half, well, firstly, sine is a half at pi over 6 and 5 pi over 6, and since its y values being greater than a half, you're looking for everything above that spot. So that's going to be from pi over 6 to 5 pi over 6. That'll be the first little cycle there, and then you just sort of add 2 pi to both of those to fit your all the way up to 4 pi. So there's the adding 2 pi, and you just do the union of those two things. Keeping in mind this time we're using rounded brackets because it was just a greater than sign, not a greater than or equal to sign. Yeah, that's it really. So anything in there you want me to clarify, let me know. Otherwise we'll do some example questions. Let's see, where was it? It was 14E, likely. No, a bit further. These ones. Okay. We'll start with, we'll start with a simple one, just 1A, so we can test our understanding, and then we'll just build up from there. Just turn the phone back on, and I shall start writing. Okay, so we're just looking for where cos x equals half. Nothing super crazy there. We're doing it from 0 to 4 pi, though, which is worth noting. Take it away. And when you have an answer, let me know. All right, actually, I'll even bring up a copy of the unit circle. You should have this memorized at some point, but just for the purposes of this lesson, I'll give you some unit circles. There's probably still one in the chat from way back when, but let's just refresh it. Get the sine and cos one and a tan one as well. Why not?
Okay, so is it pi over 3, 5 pi over 3, 7 pi over 3, and 11 pi over 3?
Yeah, that's precisely it. Yeah. So, as a quick thing for everyone else, you're fundamentally just looking for where cos equals a half. Cos is the x, that's going to be the pi over 3 spot there, 5 pi over 3 spot here, and then just adding 2 pi to both of those. Yeah, that's about it. Let's make it more complicated. How much further can it go? Yeah, okay. 7. Well, we just did cos. Maybe we'll do sine this time. 7a. I'll write it out. Sine 2 theta equals negative a half. And we're doing that for theta between 0 and 2 pi. And I'll leave that in the chat as well. 7a.
Chris, is it 7 pi over 6 and 11 pi over 6?
Um, kind of. Those will be the first two solutions. Yeah, there's a
Oh,
bit more to do.
because of the 2 theta, do we need to like now divide them?
Yeah, divide them through. Absolutely.
But wouldn't that also mean like we probably have more solutions that fit into domain as well?
Sure does. Yeah.
Yeah, right.
So the basic rule of thumb is whatever the coefficient is, you effectively double your domain. In this case, it is literally doubling domain because there's nothing else there. When you have horizontal translations, it can throw it off a little bit.
Um, 7 pi over 12, 11 pi over 12, 19 pi over 12, and 23 pi over 12.
Yeah, precisely. So yeah, again, pretty much as I described, very similar scenario, except that 2 theta meant we had to effectively find twice the number of solutions and then halve the ones that we did get. Instead of being all over pi over 6s, it was all over pi over 12s. Cool. Okay, that's composite functions. I did see there was one bit tougher, which now puts it between negative pi and pi. So let's try... Damn, no tans here. Oh, we'll do another cosine. Do 5a. So 5a was cos x equals minus 1 on root 2. X element of negative pi to pi. This is a bit tougher for two reasons.
Chris, wouldn't this be like a value that like we don't see on our unit circle?
Yeah, so that's one of the things I'm pointing out as one other reason why this might be hard. This does
Yeah.
exist on the unit circle, just not as you normally anticipate it. What could we do to the value that we do have to make it look like one of the ones that are on there?
Could we rationalize it?
Rationalize denominator. Yeah. How do we do that?
We'll just multiply by root 2 over root 2.
That's it. Yeah. So now we're going to have negative 1 times root 2 over root 2 times root 2. We're just chucking a root 2 in the top and bottom. And then from here, negative root 2 on top. And then whenever you have square roots, same value, they just cancel down. Now suddenly, you can spot that on the inner circle.
3 pi over 4.
3 pi, hang on. Yeah, 3 pi over 4, that's one of them.
But the next value is outside of our domain.
It is if you go in a positive direction, yeah. So that'll be the largest of our angles. Remember, domain is negative pi to pi though, not 0 to pi.
All right. Okay. Is it negative pi over 4?
Not negative pi over 4. negative pi over 4 would put it in quadrant 4. So negative pi over 4 would be down here, whereas you want to be here and here. Could we got negative pi? Hang on, I'm just reading this one here. Are you saying plus minus pi over negative pi plus pi over 4? Yeah, that works. Negative pi plus pi on 4. Yeah, because you're starting at, to draw that out a bit, you have negative pi and then plus pi over 4 goes in that direction. So there's your negative 3 pi over 4. So effectively the two solutions you want there are 3 pi over 4 and negative 3 pi over 4, or you could just say plus minus 3 pi over 4 there. Clear enough? I did get what you meant there, right, Pia? Yeah, awesome. Okay, cool. So that's that one. Fundamentally, you're just going in a positive direction and a negative direction, or you could do the symmetries of the unit circle thing that Pia was suggesting. That's pretty much as complicated as this chapter gets, which is interesting. There's no tan there. I guess it'll come later. Let's see, which else is for this? There was EGM I mentioned. Where's the... That's just symmetries, that's sketching. There's got to be something in the tan here to solve. Yeah, here we go. Now we can do some tan. So, yeah, this will be another refresher on the negative pi to pi situation. So let's say, yeah, why not? We'll just do 3a. Put that in the chat, 3a. And that is 2 tan 2x equals 2. And we're doing it from negative pi to pi. pi on 8, 5 pi on 8, and negative 3 pi on 8. Yeah, that's 3 of them. There is one more that's left to go there. So I'm assuming you may not have changed up
Chris,
domain.
is it?
Yep.
Oh, no, I'll jump the domain as well.
Yeah.
I was about to say negative 11 pi on 8, but no, it's not right.
Yeah, okay, that's a bit too far then. Yeah, so to get around any of this like confusion around how many solutions, that's why I recommend the substitution method. You can just keep going like further than you expect and then cut some out. That's fine. So I guess it's a question on what seems like it's less time. Do you just solve more and then cut off once you see it's too big, or do you fix up domain a bit and then that's the time there rather than cutting? It's probably equivalent, to be honest. Yeah, at least as far as time spent. BSP, you've got almost all those. There's just one left to go.
Chris, is it negative 7 pi over 8?
Yeah, that's the last value there, negative 7 pi over 8. For anyone who might still be a bit lost, first things first, get the tan on its own. So you got your tan 2x equals 1. You just want to figure out where tan is equal to 1 on the unit circle. If you look at, well, one of my provided unit circles, tan is going to be 1 at the pi over 4 and 5 pi over 4 spots. And then from there, it's just a matter of doing some rearranging, going backwards, forwards, so on and so forth. To get around any domain issues, I might be doing u equals 2x, and therefore I'd have tan of u equals 1, and you would do it for u is an element of negative 2 pi to 2 pi. That way you know you're looking for 2 solutions in the positive direction, 2 solutions in the negative direction. But of course you could just solve a bunch of them and cut out if you need to. Anything to clarify further there, let me know. Otherwise, we'll move on to general solutions. Okay, so the first one, we'll just stick with, initially we'll just stick with find the general solution, then we'll answer the second part of it, which is hence find. So this will be question 3. I'll have it written out as well, which is y equals 2 cos 2x plus pi over 4 equals root 2. If you're trying to go the route of fully simplifying this one, I know I said cosine could be, you could chuck a plus minus in there. It would seem to be the case that anytime you have a horizontal translation in there, it kind of messes up that plus minus approach. So this one does in fact end up with its fully simplified solution as two separate equations, even though it is cosine. Yeah. Was just doing that off the side just because, yeah. How's progress? Where are we at, broadly speaking?
Is one of them like pi on 4 plus 2 pi n
4 plus 2 pi n. Oh, initially, yeah. Yeah.
for the general solution?
Yeah. So it won't
I did
be final answer, but yeah.
I did the also I did the rearranging like by substitution.
Yep. So
Yeah.
that makes sense. You've got u equals pi over 4 plus 2 pi n. That'll be one of
Yeah.
them. Yeah.
And is the other one negative 3 pi over 4 minus 2 pi n?
Negative 3 pi over 4. Negative 3 pi over 4 would put that in quadrant 3. So that's a bit off. You'd want it in quadrants 1 and 4. So you could say negative pi over 4 instead if you wanted to use negatives. Or if you wanted to use positives, you could do the 7 pi over 4. Either of those work. So pretty much what's going on is you do your rearranging, so you're looking for where cos of something is root 2 on 2. That's going to give you the u value is equal to, you could have your plus minus pi over 4 if you want to do both positive and negative, or the alternative, with the 2 pi n, of course. Or the alternative would be the positive pi over 4 plus 2 pi n, and then the positive 7 pi over 4 plus 2 pi n. Either of those will get you there, where u is 2x plus pi over 4. Cool enough to go off of, or does anyone want me to continue writing from here?
Hey Chris, I got new domains after like rearranging. I just wanted to check if they're correct.
I can tell you they're not, because there is no domain for this one. Unless, oh, actually, did you mean for the...
Yeah, for the next part.
Yeah, for the next... Okay, yeah, sure. I don't have those in front of me, but as long as... Okay, let's hear them.
I just subbed like negative 2 pi into the brackets,
Yeah, so
and
you... Mhm.
I got negative 15 pi over 4 and 17 pi over 4.
Negative 15 pi over 4, 17 pi over 4. Yeah, I mean, you subbed in negative... You subbed in your two values, positive and negative 2 pi, into the x spot on the u.
Yeah.
Yeah, okay. I'll solve that on my own so I can verify that answer, but that is what you do. Yeah, so I'll just make sure that's good. I'll do that off screen a little bit. Actually, no, I can do it on here. Why not? U equals 2x plus pi on 4. And then, yeah, sub those two in. Yeah, I think those are good. So for the second part of it, it would be, yeah, your u would be between negative 15 pi over 4 and 17 pi over 4. But yeah, before we go further with that, curious to hear general solution first. And the reason why getting the general solution becomes a bit more important is because you'll find you don't necessarily, for general solution kind of questions, need to fix up domain, and you'll see why once you have the general solution. It's good to have it, but yeah. This one does take a bit of a time to solve. Just checking in no one's like super stuck. Otherwise yeah, if anyone's stuck, I will start writing this out, just so we at least have a solution by the end of class. Just let me know if you want me to start writing. Stuck? Yeah, okay. So I like that you've used the knowledge from before to try and update the domain here. I will say first thing you want to do to get straight is get the general solution straight. And you've kind of done that good with the U values here. But if you just stick with U here, it's going to be a lot of messing around. So it is good to try and get this back in terms of X. So if we were to try and get that back in terms of X, we're just going to replace the 2x and the plus pi over 4 into both of those spots. So you got 2x plus pi over 4 is now equal to pi over 4 plus 2 pi n. And you've got the 7 pi over 4 plus 2 pi n. If you are working with negative pi over 4, that's fine. That also works. There's no issues with that. I'm just going to go with this one because it's one possibility. Next, we're just going to unravel this, which means subtract pi over 4 from both sides. That's going to give you 2x equals 2 pi n. And then going backwards on this one, so 6 pi over 4, which is 3 pi over 2 plus 2 pi n. Then from there, a further divide by 2. That's going to give you x equals pi n and 3 pi on 4 plus pi n. Reminder that you divide everything in there by 2. Now, this gives you a general solution for potentially every value around all the iterations of the unit circle. We want to just go between negative 2 pi and 2 pi. The way you actually use this is you sub in different n values starting at 0 and then plus minus 1, plus minus 2, and you just keep going until you get too far. Then you cut some off. So having this here could be nice, but at this point you're better off just probably subbing in just n values until you make it. So for example, first thing up, n equals 0. That'll be the first iteration forward. So that will be x equals 0 from there, and x equals 3 pi over 4. Those are your first two solutions. Then you could do n equals 1. That's going to give you the x equals pi, and it's going to give you the 3 pi over 4 plus pi, 4, 5, 6, 7. So 7 pi over 4, which is pretty close to 2 pi. If you want, you can try and find another solution after that, but I'm pretty confident there's not going to be one. It's only pi over 4 removed from the n there. And then lastly, negative 1. So you just sort of go either side. If it's an even domain, negative 2 pi to 2 pi, you can be pretty certain you want to go spread out from n equals 0. That's going to give you negative pi and then negative pi over 4. There's probably one more still in here, if I were to guess. So we can check n equals negative 2. That's going to give you x equals negative 2 pi, which is a bit too big, given that we had circle brackets instead of square brackets. And then subbing in n equals negative 2 into this will have a solution. Yeah, so negative 2 pi, so negative 8, 7, 6, 5, negative 5 pi on 4. So in total, that one's a little bit too big. We're pretty certain this is as big as it's going to get. That's supposed to be a 5. And then, yeah, that'll give you all those solutions there. Just double checking I got all of them. 0 pi, 3 pi over 4. Yeah. Negative pi over 4, negative pi, negative 5 pi over 4. Yeah, okay. So that's the approach I recommend. I don't think having this domain helped a whole lot. I mean, yeah. Because the alternative would have been, instead of getting everything in X, you do exactly this in terms of U, and then for each one of these solutions, you do this unwrapping. And that's a lot of additional work. Whereas if you do the unwrapping early, you only have to do it twice, and then everything's already in terms of X. So if you try to do it all in terms of U, it would still work. It just would take a significantly longer significantly longer time to do it. That's about it. If you want me to clarify that any further, feel free to stay behind and ask questions. Otherwise, take care.
Hey Chris, I just had a question. Like, would we in like a test or an exam usually see like a general solution question and then it asks us to like find the values between a domain?
It's pretty rare to get it at all. I've seen
Because
at
like
least. Go ahead.
yeah, like I was kind of like I kind of got confused. Like it was asking like a general solution and then asking for like the solutions inside a domain.
Yeah, I mean, all it's trying to do is show you how to use a general solution if you're given one. That's pretty much it, really. I've seen one exam question which has asked for a general solution, and that was it. Um, at least as far as that question goes. It probably then, in an extended response, then asked, hence find solutions, or not even. It would say, like one of the things they do is ask you to sketch these circular functions, um, and what the general solution would do if you already had it from a previous question is it would either tell you x-intercepts or maybe a y-intercept, depending on whatever the thing equaled. Like in this case, it equaled root 2. So basically, it would tell you where y equaled root 2 on that graph. So they do have little cheeky ways of applying the general solution, but they never force you to use the general solution to solve something else. You can just go and do it as you normally would.
Cool.
Clear enough?
Yeah.
Sweet. Anything else I can help you with?
Um, are we gonna like start doing like sketching of these graphs just in case?
Are we going to
In part
start
for
doing
today.
sketching? Let me see. So we just did week 6, week 7, circular function 7. I think that's symmetries. No, sketching sine and cosine. Yeah. So next week for this class, it'll be sketching. Yeah.
Right. Yeah, because when I was in year nine, I did circular functions like just on the side
Mhm.
outside of school, and like I it wasn't like that clear, but now like I'm getting to like learn it a little bit better.
Yeah, okay. So if you're looking to get a head start on that before the class, then obviously there's the written stuff and the recorded stuff. I think I've even done a class on it. Yeah, I've done a group class on this before for sure.
Yeah.
So if you want to revise those are also there for you, should you wish.
Yeah. Cool. Thank you.
Otherwise, same time tomorrow. Same time next week.
Yeah. Cool. Thanks.
Take care.